Like I said, today is all about inverse functions, but specifically today, we're just going to be looking at what makes an inverse function an inverse function. Like, what are the properties between its original and its opposite? All right, how do they connect? So, that discovery was kind of the lead in. So, you already noticed that the graphs look like they're flipped, they're going in different directions, the x and y values flipped, all that good stuff. All right. Now we're going to actually look at the actual rules. So, again, the idea of inverses or opposites. So, if you ever hear the word inverse, opposite should be the first thing that pops in your head. It's really important to mathematics because essentially you use it all in some shape or form. So, for example, solving equations, you do inverse operations, which just means you do the opposite operation to undo what's already there. Okay. Now, there are rules governing the reversals of themselves that can be functions, and we're going to talk about them. So first off, let's look at exercise 1. So they gave us two functions, f of x and g of x. Now, letter A, they asked us to calculate what f of 5 is and what g of 11 is. Now, we talked about this a lot last week. If we see f of some number, what does that mean we do? We plug them in for x. So I'm going to plug in 5 into f of x, so the yellow function. So I get 3 times 5 plus 7 all over 2. And I'm just going to do a very quick calculation because it's fairly straightforward. So 3 times 5 is 15. What's 15 plus 7? 22. So I have 22 over 2. What's 22 divided by 2? 11. So f of 5 is equal to 11. Then I'm going to do g of 11. So again, I'm plugging in 11 in for x and g of x, so the green function. So I would have 2 times 11 minus 7 over 3. So let's just do some quick calculations. So 2 times 11, 22, minus 7, 15. So I have 15 over 3. What's 15 divided by 3? 5. So I had inputs. These are my two outputs. What do you notice about my two answers? They flipped from what I put into the other function. So for example, I got 5 when I put 11 in for G. But if you look at F, when I put in 5, I got 11. They switched. All right. Because X and Y switched, we're thinking that F of X and G of X may be inverses of each other. All right. But we can't just go off of one example because coincidences do happen. So let's try another one. So we're going to do the same thing again, but this time with f of 0 and g of 7/2. All right. So if I'm doing f of 0, that means I'm going to have 3 times 0 plus 7 over 2. Well, anything times 0 is 0. So I'm just left with 7 over 2. I'm just going to leave it like that. Then g of 7/2. I'm going to have 2 times 7/2 minus 7 all over 3. Well, if you multiply a whole number by the same number in the denominator, they essentially cancel out. So I'm left with 7. So 7 minus 7 is just 0. Anything going into 0 is always 0. So these are my two new outputs. Did they flip based off of the inputs that I put in? Yeah, they did. I put in 0, got 7/2, put in 7/2, got 0. All right, so they flipped again. So one thing that we can say about inverse functions is that if any takeaway from inverse functions that you have, the biggest thing about inverse functions, switch x and y. All right, that's the biggest thing you got to know with inverse functions. You switch x and y. All right. Now, another thing about inverses is that they truly do undo each other. So Letter C is talking about a composition of functions, and we read it as f of g of negative 1. Meaning, if we start from the inside and work our way out, we're going to find g of negative 1 first. All right? So we're going to plug in negative 1 in for g. So I have 2 times negative 1 minus 7 all over 3. So what's 2 times negative 1? Negative 2. What's negative 2 minus 7? Negative 9. So I have negative 9 over 3. What's negative 9 divided by 3? Negative 3. Now, I'm going to then take this negative 3, plug it back in for g of negative 1, meaning I'm now finding f of negative 3. All right? So I'm going to plug in negative 3 in for f. 3 times negative 3? Negative 9 plus 7? Negative 2 over 2. What's negative 2 divided by 2? Negative 1. Now, even though we did 2 different evaluations, it's all within the same problem. So this would have been the first step. This would have been the second step to solving. So negative 1 would have been our answer. What do you notice about our answer? Say it again. Right. It's the same thing as what we initially put in. All right. So we initially put in a negative 1. Our final output was negative 1. So another property of inverses is that if you took a composition of the two, you'll end up with what you originally started with. All right. So let's check this with f of g of 5. So without doing the calculation, what do you think my answer is going to be? 5. So we're thinking my answer is going to be 5. Well, let's check it. So if I do g of 5 first, I'll do 2 times 5 minus 7 all over 3. So 10 minus 7 is 3 over 3, so that's 1. I'm going to take this 1, plug it in for g of 5, so now I'm finding f of 1. This would be 3 times 1 plus 7 all over 2. So 3 times 1 is 3, plus 7 is 10. 10 divided by 2 is 5. Did I get what I originally put in? Yeah. I originally put in a 5. My output was also 5. So, without doing a calculation, f of g of pi, what should my answer be? Pi. Now, if you don't believe me, I actually did this in my previous class. So, let's just check to see if it'll actually be pi. So, first I have to do with g. So, I do 2 times pi minus 7 divided by 3. All right, that I get this big number. I'm not going to figure out what that is. Then I'm going to take that, plug it into f. So I have 3 times second answer. So it takes what I have up top plus 7 divided by 2. Is it true that 3.14159, et cetera, is pi? Yep. So we put in pi, we got out pi. All right. Now, was I going to do that by hand? Heck no. All right. But all you need to know is that if you have a composition and they're inverses, whatever you originally put in, that's what you get out. That's with inverses only, though. All right, so be careful about that. It's with inverses only. So we can confidently say that f of x and g of x are inverses of each other. So f of x and g of x are inverses, meaning that they are opposite functions of each other. Now, like I said, inverses literally undo one another. So, for example, like if we want to take real world example, if you tied two knots, right? So, let's say a function tied two knots, that's what it did. Its inverse function will untie those knots, all right? So that's what it means we are undoing. They're essentially like literally, they're taking each other apart. So when it's saying f of a is equal to b and g of b is equal to a, all that means is that's a bunch of math verbiage for switch x and y. Biggest thing, switch x and y. So for example, if you had f of x and you put some point on f of x, so let's say some point on f of x was xy. That means some point on f negative 1 of x, or the inverse, will be yx. So if you have a point xy on your original function, its inverse will contain the point yx. Like I said, if anything comes from this lesson, when it comes to inverses, that right there is probably the biggest piece of information you need to know about inverses. All right? So for example, if I asked you to tell me if two functions are inverses of each other, really all you would need to do is put them in Desmos, get a couple of points, and see if you have points, like at least two or more points, that are literally just the x and y values flipped. And then they would be inverses of each other. Also, when we do this tomorrow, so when we solve for the inverse function, the first step is to switch x and y. All right. So for exercise 2, if I'm giving the point negative 3, 5 on f of x, what point must lie on its inverse? So take a minute. Remember, it's all about switching x and y. As a show of fingers, which answer choice do you think would be the inverse? So again, switch x and y of the point. So in reality, you're just flipping this. So as a show of fingers, which point do you think would be on that inverse function? Ready, go. Right, it would be 3. So when I say switch x and y, I literally mean flip the numbers. So if 5 was in the y, it's now in the x. If negative 3 was in the x, it's now in the y. That's all I mean when I say switch x and y. I literally mean switch them. All right? Yes, sir. I'm about to go on break. Can you wait till then? All right. Now, inverse functions have their own special notation. We already saw this a little bit. So remember, if you're given a function y equals f of x, its inverse is represented as y equals f negative 1 of x. Guys, heads up. Come on. So let's do example 3, and then we'll go on a 5-minute break. Okay. So if I'm given this function, which is graphed here, so this graph over on this side is of the current function that they gave us at top. We're going to evaluate the inverse of that function, but we don't know what the inverse function is. So using what we do know about inverse functions, what do you think is going to happen? So let me ask you guys this. If this is the x value of the inverse, this is the x value of the inverse. What is 2 for the regular function, so f of x? If 2 is the x value of the inverse function, what is it for the regular function or the original function? Well, I'm asking what value it is. So is it the x or y value for the regular function? That's what I should say. It'll be the y value. Because remember, we switched the x and y. So if that's the x value for the inverse, it's the y value for f of x. And that's also true for f negative 1 of negative 4. If it's the x value for the inverse, it's the y value for the original. So if we want to evaluate it, we're just going to use the graph, which gives us f of x. And we're going to find where y is equal to negative 2. So when y is equal to negative 2, that's, or not negative 2, positive 2, that's right here. So we're looking at this point specifically. So if I'm given the y value of f of x, that means my answer is the what? The x value. So this point is the point 6, 2. So what's my answer for f negative 1 of 2? 6. So f negative 1 of 2, we only care about the x value. So that would be 6. What about f negative 1 of negative 4? So we're finding where y is negative 4 on the original. So that would be right here. So this point right here. So what's the x value of this point? Negative 3. So this is the point negative 3, negative 4. So what's my answer? Negative 3. Good. So guys, if they ask you to evaluate an inverse, but they don't actually give you the inverse function, but they give you the original, typically they'll give you a graph with that, or it's something you can put in Desmos. If you got the x value of the inverse, you have the y value of the original. And so you just find whatever you're missing. Does that make sense? Yes, no, maybe. All right. What about the y-intercept of the inverse? So think about it carefully. How do we typically write the y-intercept as a point? So it's where it crosses the y-axis. How is that typically written as a point? The x value is always what? For the y-intercept. It's always 0. So when we're talking about the y-intercept, we're looking for a point 0 some number. Now, if that's what we're looking for the inverse, what are we looking for in the original? If we switch x and y. So that means in the original, we're looking for, if we switch x and y, so that'll be some number 0. Well, what's that called? So we're not looking for the y-intercept anymore. We're looking for the x-intercept. Good. So here's my x-intercept. This is at the point 3, 0. So what's my y-intercept for f of negative 1 of x? It's 3, but what's it as a point? 0, 3. No, you're right. So this will be my y-intercept for f of negative 1 of x. Now, last thing it asks us to graph f negative 1 of x. We already have points that we can graph. So we have the y-intercept, and then we have these 2 points here. So if I make a quick table x, y, this will be 0, 3, 2, 6, negative 4, negative 3, which I'll just graph very quickly over here. So I have 0, 3, 2, 6, negative 4, negative 3. Technically, but the table is just to kind of organize my points. It doesn't really have to be in numerical order. So this would be f negative 1 of x, and this right here is f of x. All right, any questions on that one? All right, so I'm going to let you guys take your 5-minute break. I'm going to set the timer. Make sure you're back before that timer's up. Also, make sure you're quiet in the hall so you don't disturb other classes.
Is your song? No? Darn. It has to be. Um, or was it a business understood? I'm hungry.
All right, guys, 5 minute breaks up. So let's get back to it. Also, thank you for being back when you were supposed to. Good job. As long as you guys keep doing that, I'll keep giving you 5 minute breaks. Not today, but for the rest of the semester. All right. So now let's look at exercise 4. So with exercise 4, they gave us the original function, which they said was x squared. They gave us its graph as well as its table. So the top table that's already filled in, that's the table that they use for the points for f of x, or x squared. All right. So if they want us to graph the inverse, first we're going to make the table. So really, what's the only thing we got to do? Flip what? The x and y. So essentially all we got to do is just switch these two rows. So what will be my x's now for my inverse? The y's from the old one. So 4, 1, 0, 1, 4. Will be my new y's now. The old x's. -2, -1, 0, 1, 2. All right. So when I say switch x and y, I literally mean switch them. All right. So now we're just going to take a minute, graph it very quickly. So I got 4, -2, and +2. 1, 1, 1, -1, and then 0, 0. So my graph will look something like this. Now, what's something that you notice about the inverse graph? What kind of happened, Jonah? It rotated 90 degrees. So we rotated 90 degrees. And I guess if we want to be specific, it was clockwise. All right. What else kind of happened? Someone else. What's something that you just notice? There's no really right answer here, but what do you kind of notice about it? Let me ask you this. We know x squared is a function, right? It passes the what test? So we talked about this last week. What test does our function need to pass in order to be considered a function? Vertical line test. So if we ran our pencil vertically across it, it passes. Is our inverse a function? No, it's not. All right. So if you go through the vertical line test for one, take your pencil, run across. Right here, we already have a violation. All right. It's here, it's here. You can also see it in the table. 4, 4, 1, 1. What's the only thing that can happen for it to be a function? Or the one thing that can't happen for it to be a function? X's can't repeat. All right. So even though this function has inverse, that inverse is not a function. All right. So it's not always true that its inverse is considered an inverse function. All right. So every function has an inverse, but not every inverse is a function. That's kind of like every square is a rectangle, but not every rectangle is a square. That kind of thing. So inverse is not a function because it fails vertical line test. All right. So that leads into the next part. this goes along with one-to-one functions. So we talked about one-to-one last week. So in order for it to be a function, cannot have repeating x's. So in order for a function to be a function, it cannot have repeating x's. Does anyone remember what the other stipulation needs to happen in order for it to be a one-to-one function? The y's can't repeat either. So that's what it means for it to be one-to-one. So, in other words, if I ever ask you, does this function have an inverse function? The best way that you can tell is if that function is one-to-one. All right. If a function will have an inverse that is also a function, if and only if it is a one-to-one function. So in other words, it needs to pass the horizontal line test. So the original function has to pass the horizontal line test as well as the vertical line test. The vertical line test is a given. If it doesn't pass the vertical line test, we don't even care if it passes the horizontal line test because it's not even a function to begin with. All right? All right. So, how do I want to go about this? All right. So here's what we're going to do for right now. We're going to put a pin in this because this is about where I stopped for my second period. I don't want you guys to get ahead of my second period. Okay. So we're going to put a pin in this. Your optional assignment for this particular lesson would be pages 13 and 14. All right. So 13 and 14 will be your optional assignment. There is a Delta Math already, but you may not be able to do all of it just yet. That'll go along with what we're doing tomorrow. Okay. So you can, you should be able to do the first 2 topics in Delta Math. So what we'll do now is that use this time, so the next 20 minutes that you have left of class, just to work on your Delta Math, so 1.1, 1.2, if you haven't finished those already. You can start 1.3 if you want. If you don't, you can work on your optional work. All right? But that's kind of how we're spending this time. Also, one last thing. This green sheet, all right? This needs to go in your journal. Does anyone have their journal with them right now? I can use it. All right. Exactly what you use your example. Okay, so here's what's going to happen. So if you're in your journal, everyone look at me right now. So in your journal, you want to go ahead and include this in. So you're at your goal sheet. Remember, the next page is 1.1, 1.2. This is going for 1.3. So this little green sheet is 1.3. So that means from your goal sheet, you're going to turn the page 1, 2, 3 times your goal sheet. You're going to paste it on the right. All right? That's where this is going to go. We're going to do this together in class tomorrow. All right? So make sure it's either pasted in your journal now or make sure you at least have it on you.
I don't understand that shelf.
They're on the shelf.
When did my blue six go over my transmission when I haven't seen food, so
I have glue sticks on the shelf.
not yesterday. Last week on Thursday. Wednesday.
Alexis, I'll be right there.